All right, what's up, folks? I've moved my computer about 3 different times now. I think I'm finally happy where it's at. Hopefully, you've got yourselves all settled and you're figured out what you're doing here with this online learning. I'm here recording you another lecture. So, what I'm going to do this week, today's lecture is on molecular orbital theory and more on that. And then with that, we're going to do molecular term symbols. So, it'll be very similar to atomic term symbols. I'm going to also post to you a number of videos on just solving approximation methods, so solving wave functions of systems that we don't have an analytical solution to. That is not my area of expertise, but I am going to post a number of short videos that I found that I think do a really good job of explaining that. But I do want to go through molecular orbital diagrams and molecular term symbols. So just as a review, we recall, so here we go, MO diagrams, okay, molecular orbital diagrams. So we recall that when we combine a 2s and a 2s, so when we make a bond out of a 2s and a 2s, okay, we make a 1 sigma g bonding orbital and a 1 sigma u anti-bonding orbital, all right? So if we combine, and so of course those are sigma bonds, right, on axis, sigma bonds. If we combine a 2pz and a 2pz, we make 2 sigma g bonding and 2 sigma u anti-bonding. All right? And then if we combine either 2px or y with another 2px or y, this is what creates our 1 pi u bonding or our 1 pi g anti-bonding. All right? So let's do 2 examples, O2 and F2. All right? And I'm going to start at the very bottom here, and we want to work all the way up. Later on, when we do term symbols, we'll only worry about the valence level, but let's just do all the way up. All right? And so we'll start. No, I changed my mind. Let's go ahead and do the valence level. I'm going to skip the 1s level. Let's start at the 2s level. So here we go. I start by making a little kind of diagram that looks like this, where each one of these wings are 2s and 2s, and hopefully you recall this from the Chem 109 days. And remember, when I combine a 2s and a 2s, right, that makes my 1 sigma g and my 1 sigma u. And of course, for each oxygen, if we recall the each oxygen's atomic configuration, right? 1s2, 2s2, 2p4. Yep. Okay. Make sure, cheat here with my periodic table. I know some of you have a periodic table. This doesn't count, right? This is the periodic table. Some of you have a periodic table on your desktop. That's pretty handy. So each one of these refers to each oxygen atom, right? So we have 2s electrons for each oxygen atom. So that's 4 electrons in total, right? So I'm going to have 1, 2, 3, 4. So that level is all filled out. Okay. Then we're going to have another level that we can make right here that refers to the 2p. And I like to draw 3 lines right in there. Okay, that's not even at all. Do over. I'm not going to stop and re-record. I'm just going to keep going. And of course, I'm using my wet erase that doesn't erase very well. Sprayed the wrong zone. That's all right, folks. Only one take. I don't got time for multiple takes here. Okay. So let's draw this a little bit better. Okay, here we go. So those are both starting at the same area. And I like to put 3 lines in there when I do 2p to remind myself that I've got 3 degenerate p levels. Okay, so this is my O2. And so because each oxygen has 4 p electrons, I'm going to have 8 in total in this diagram. And so now I have to go through all these combinations of if I'm pairing up 2pz's or 2pxy's. And so recall last time, the 2 sigma state from combining 2pz's is the lowest in energy. And as it turns out, the 2 sigma u for oxygen is the highest in energy. So then what that means is the px and py states, in other words, that make the pi bonds, all right, they end up being sandwiched in between for O2 and, as it turns out, also for F2. And so this level right here becomes my 1 pi u bonding, and this level right here becomes my 1 pi g anti-bonding. And I've got 8 electrons that I need to populate here, right? Each oxygen had 4. So that's going to go 1, 2, 3, 4, 5, 6, 7, 8. And notice I put them in one at a time. Okay? And so now I would say that my this is my oxygen atom electron configuration. My O2 molecular electron configuration would then be, and I'll just write down for this valence level here, 1 sigma G2, 1 sigma U2, right? So 1 sigma G and there's 2, 1 sigma U2, 2 sigma G2, and for now I'll just write that as 1 pi U4, but we could specify if this is X and Y. And we don't know which one of these are X and Y, but it doesn't matter. One is X and one is Y. And we'll see why that matters soon. And then finally, 1 pi G2. Okay? And so great. So let's work on F2, and we'll still do it together, and we can copy this over directly. Okay? So we're going to copy that 2s level, and we're going to copy that 2p level, assuming that I draw it correctly here. Okay, 1, 2, 3, 1, 2, 3. So 2s, 2p, 2p, 2s. And we remember that each F atom is going to be, let's just do it from the bottom, 1s2, 2s2, 2p6. All right? Each F atom has that configuration. And so I'll draw in my pi bonds here. Okay, so this is my 1 sigma G, my 1 sigma U, my 2 sigma G, my 1 pi U, my 1 pi G, and my 2 sigma U. All right? And so now filling this thing out, I know that in my 2s level here, each F atom has 2 electrons. So this has 2 and this has 2, so that gives me 4 in total. 1, 2, 3, 4. Okay, and then now I know that each F atom has 6 p electrons, so I'm going to have 12 in total up here. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What did I do wrong here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, you know why? Because, I'm not doing F minus. I'm just doing a regular old F atom. Haha! 1s2, 2s2, 2p5. You guys are probably like, what the hell, isn't he a chemistry professor? Yep, I am. We all make mistakes. So that means 10 electrons we have to fill out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There we go. That's the F2 MO diagram. And then the last thing that I'll summarize on this board here before I erase, bond order. All right, bond order B equals 1/2 times the quantity N minus N star, where N is the number of bonding electrons, and here this is the number of anti-bonding electrons. So now from these MO diagrams here, I can count up all this stuff and then predict how many bonds it should have. So if bond order is 1, it's a single bond. If bond order is 2, it's a double bond, and so forth. So now, and I'm just going to look at really my topmost level, because if you think about it, on this 2s level, well, there's 2 bonding electrons, but 2 anti-bonding electrons, so that zeroes out, right? So now let's look at this one here. So count up my number of bonding electrons. 1, 2, 3, 4, 5, 6. Okay, so that's 1/2 times 6 minus, and then anti-bonding electrons, 1, 2. Okay, and so 6 minus 2 is 4, times 1/2 equals 2, and we know that oxygen has that double bond with the 4 lone pairs, like that. All right. Okay, so then now, if we go do the same thing with F2, all right, I've got 1/2 times 1, 2, 3, 4, 5, 6 minus 1, 2, 3, 4, and 6 minus 4 is 2, times 1/2 is 1, and we know that F2 has that single bond with lone pairs surrounding it. Okay, so that's great. So now what I'm going to do, I'm going to add a layer to this, and we're going to do now the molecular term symbols. Really quick, sorry, one last thing I forgot to write. Let's write the molecular configuration for F2, right? 1 sigma G2, 1 sigma U2, 2 sigma G2, 1 pi U4, I'm running out of room, 1 pi G4. Okay, great. So now, keep all this in mind. Maybe this was a review from the Chem 109 days. Maybe it wasn't. Oh, I did remember one last thing, sorry, that I wanted to go through before I switched into term symbols. Okay, so we talked about this with O2 and F2. And keep track here the order, right? The way we're doing this for O2 and F2, 1 sigma G, 1 sigma U, then 2 sigma G, then 1 pi U, then 1 pi G, then 2 sigma U. The situation changes with nitrogen. Okay, and so let me grab a document real quick here and show you. So I'll bring this over now. Let's see here. Yeah, I'll just talk about this right here without my floating head in the way. So now, if you look at what we did here with O2 and F2, right? There's that order, 1 sigma G, 1 sigma U, and then right here, look, there was that 2 sigma G. Actually, yeah, I changed my mind. Let's bring it all over to the same desktop here so that we can do this. Here we go. So, right, so there was 1 sigma G, 1 sigma U, 2 sigma G, 1 pi U, 1 pi G, 2 sigma U. Look what happens as we move away from F2 and we move towards, let's say, nitrogen, right? The case with oxygen is still the same, but you notice how all of these energies are shifting. There's a huge change in the energy of the 2 sigma G, right? The 2 sigma G really drops significantly in energy in O2. And that's actually due to S and P mixing. So the order switches when you have less than half-filled orbitals. So nitrogen is right at your half-filled orbital, okay? And so that's where it goes to where it switches. And then once it's more than halfway full, that 2 sigma G energy level really drops in energy, and that's because the S and P mixing becomes more favorable. So keep track of that, okay? Oxygen and nitrogen have this order, but with nitrogen and carbon and so on, the order switches. So keep that in mind, because that's going to change not only the diagram you get, but the term symbol that you get as well. Okay, so now I'm going to go ahead and erase, and we're going to come back to these examples of O2 and F2 and N2 and so on. And we're also even going to make excited states out of those. And so we'll talk about what happens to the diagrams with the excited states, and we'll also talk about what happens with the term symbols and how we use those in spectroscopy. Okay, so let's get some space cleared up here. Okay, so now if we switch over to talking about molecular term symbols, let me dry this a little bit better. Okay, so molecular term symbols. And I'm going to go through these here on the board, and just like I did with atomic term symbols, I have another supplemental document that I'll review that I think will give you a little bit better, just provides more supplemental information. So the symbology of the term is the following. 2s plus 1, hopefully that looks familiar. That's our multiplicity. Down here below, we're going to put P for our parity. And so that's going to be either G or U, gerad or ungerad, even parity or odd parity. And then also up here, we're going to put either a plus or a minus, but only for certain states. Okay? And also, this is just linear diatomic molecules we're doing. So we're only going to keep it simple for now. I'll show you a few examples of some heteronuclear diatoms, but for the most part, we're just going to focus on homonuclear diatomics. All right? So lambda, this is analogous to our L in atomic term symbols, our main term. And lambda will take on values 0, plus minus 1, plus minus 2, etc. And there's significance to the negative signs, okay? And if we look at just the absolute value of lambda for 0, 1, or 2, we would call those sigma states. That's a capital sigma, right? Capital pi, pi states, or delta states, okay, for 0, 1, or 2. And so the way that we sum up lambda is by summing up all of the little lambda values. And so those little lambda values refer to bonds, all right? So a sigma bond has a little lambda value of 0. A pi bond has a little lambda value of 1, and those are the only bonds that we're going to worry about, sigma bonds or pi bonds, okay? So for example, if I go to the molecule H2, H2 is a very simple molecular configuration of 1 sigma G2, right? And so if I was summing up lambda from this, I have 2 electrons, and each one of those are in a sigma bond, okay? So, and sigma bonds have lambdas of 0, so that's 0 plus 0, and that equals 0, so that tells me it's a sigma state. Okay, now, for example, if I'm going to go back to my O2 example here, and I'll just remind you really quick. With my O2 example, what I'm most interested in, let's see if I can put this down. Yep, if you remember this here. What I'm most interested in are these outermost electrons, okay? All of these things are going to be closed up if you think about it. So when I'm dealing with O2, term symbol, I'm looking at those just uppermost levels, which is the 1 pi G2. All right? That says 1 pi G2. But now what I have to consider, if you remember from my diagram, that was split. And it was split between the 1 pi, let's call it X G 1 for 1 electron, and 1 pi Y G 1. Right? So our 1 pi G state, right, they weren't bonded. It wasn't a singlet state. It was a triplet state, right? They were separated. And so now what that means, when I go to calculate this lambda here, it doesn't matter which one you ascribe a negative or positive value, but the fact that they're in different orientations, they have a different sign. So that means there's actually a different angular momentum as a result of being in those different orientations. So if, let's say I call the X positive 1, then the Y is -1. And so that means this is still equal to 0 and thus still a sigma state. So watch this. You have to be very careful. This is going to get tricky. So that's why I think doing those diagrams is going to be a good review for getting the molecular term symbol correct. Okay, so now if we were to keep going down this example of doing, let's keep going down H2, okay? So we know that it's a sigma state because we calculated it right there. And so now I have to consider my S, okay? And so my S is, right, I'm just going to sum up all of the other values of S, okay, and so forth. And with the H2 molecule, we have 2 of them, and we know that they're paired up. So right away, if you recognize that that's a singlet state, you can just automatically make that a number 1 because it is a singlet state. But if you didn't recognize that, right, remember it's those 2 electrons are spin up and spin down. So that's a +1/2 and a -1/2, giving you an S of 0, and 2 times 0 plus 1 equals 1. So that's where we get that it's the singlet state. And then continuing along, okay, with my parity right here for P, okay, if we have a G times a G, that gives me a G. If we have a U times a U, that still gives me a G. So think of it as a positive times a positive gives you a positive, a negative times a negative still gives you a positive. But if you have a U times a G, that gives you a U. A positive times a negative is a negative. So now back to our O2 example, it was 1 sigma G, or excuse me, our H2 example, 1 sigma G2, they're both G, Girard symmetry. G times G gives me a G, voila. And then finally there's that plus minus state. We only do plus minus for sigma states only, okay? So let me write that down here, sigma only for this plus minus configuration. And when you have, when the sign of the wave function doesn't change signs as you cross a plane, it's a positive sign. If the sign changes when you cross the plane, it's going to be a negative sign, and I'll show you an example of that. For O2, because this is all symmetrical, it's all sigma bonds, right? There's no pi bonds or pi electrons. Then we automatically put a plus right there. And as it turns out, all closed shell homonuclear diatomics have the 1 sigma G plus state, okay? And so I'll go through a list of those in a moment here, but right, there's our H2 molecular term symbol. So now what if we were doing H2 plus, okay? So that's a 1 sigma G1, so we took away one of those electrons. So then that means that it's 1 sigma bond, so that's a lambda value of 0, which means that it's the main term is sigma. It's a G, and there's only one of them there, so it's got to be a G. Hopefully you recognize from atomic term symbols, that's got to be a doublet state because it's just one unpaired electron. But if you didn't recognize that, right, it's S, little s equals 1/2. So then 2 times 1/2 plus 1 equals 2. And then finally, because that's still like no pi bonds or anything, no change of symmetry, it still has that plus state, doublet sigma plus. Okay, so now what about back to our O2 example? Okay, so, and let's see, we recall here that it was a 1 pi G 2, where those are split between the pi xy and the pi xg and pi xy. Okay, so if you look at that, for example, what that looks like, this symmetry operation that I've been talking about here, I'm going to kind of draw a weird coordinate system where here I'm going to call this the x, this the y, and this the z. And remember, z is our internuclear axis, right? So my pi x kind of looks something like up here. So pi gx, and it's plus minus about the y plane. So that's got a negative symmetry operation because it's changing sign as I cross, okay? But now if I look at the pi y, so remember, in and out of that same plane, okay, plus minus, if I cross the same plane for the y plane, it's not going to change signs. And so now what that means, what you have here with this pi xg, pi xy, and it doesn't matter which one, or I guess the way I've drawn this, right, this would be a negative, and this would be a positive. So a negative times a positive equals a negative. And so now going back to my O2 state, right, we said that that's a sigma. This symmetry operation tells me that it has to be a negative right there. Both of those are g, so a g times a g gives me a g. And then finally, you might recognize, again from our atomic term symbols, that they're both spin up. They're not paired up. So that makes it a triplet state. Okay? And so if you didn't recognize that, right, it would be 1/2 plus 1/2 to equal 1, and then 2 times 1 plus 1 equals 3. So then now, there we go. That's my O2 state. Triplet sigma g minus. Okay, so I'm going to go through and I'm going to do one last example, and then I'm going to give you some examples to work on. All right, and let's see here. Okay, let's get this erased. Okay, great. So then the last thing that I'll talk about, in the event in which we have spin-orbit coupling, and really, if you recall with spin-orbit coupling, that's predominantly referring to the j equals 1/2 or the j equals 3/2 states, which is typically observed in doublets. That's where we're doublet states is what we're interested in. And the molecule, I'll give you an example of this, is NO, the NO radical. It's got 11 electrons, okay? Its configuration looks something like this. And in the next coming lectures, I'm going to talk about more details of how we do the heteronuclears, why we know one is not at the same level. So let's see. Down here would be the oxygen side, and this would be the nitrogen side, and 2s and 2s, all right? And so now it kind of looks contorted. So usually the more electronegative element is lower, 1, 2, 3, 1, 2, 3. But again, we're going to go through that in more detail on the next lecture. Okay, and that's 2p, and that's 2p. So now with the 11 electrons here, we've got the pi states right there. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so, and that outermost level makes it, so again, this is 2 sigma g, 2 sigma u, or rather, excuse me, 1 sigma g, 1 sigma u, right? Okay, 1 sigma g and 1 sigma u, and then now 2 sigma g and 2 sigma u, and that makes this most outer layer 1 pi g. So my most outer layer for NO is 1 pi g1. Okay, and if I go to do that term, right, my lambda Okay, I've got, it could be plus or minus 1. It doesn't really matter, but what's important is that it's 1. Because remember, I really do the absolute value. That's what's important. So that's the pi state. Okay. And then now you might recognize that because it's one unpaired electron, that makes it a doublet. It's a doublet state. And then now we might decide that we're going to do G right here, which would be correct. But as it turns out, this doublet pi state, there's spin orbit coupling involved with that. And so that's where it becomes important to note a new term here, omega. And that omega is the value of lambda plus the value of s. Where then this value of s, I'm going to kind of draw this s differently. This value of s is the sum of all our s's. And so because that means this big S is plus minus 1/2, for this system, our omega, right, with that being 1, is the 3/2 or the 1/2. So this is equivalent to J in atoms. And so what that means is my NO can adopt a doublet pi 3/2 or a doublet pi 1/2, and this is the lower energy state. But all the same, it would have this doublet configuration for the ground state of NO. Okay, so now I'm going to go ahead and erase this. I'm going to give you some things to do. So we're going to work on making excited states and how we know which one is the correct energy, which I think this gets kind of fun because, again, we're breaking the rules here of what you learned in Gen Chem and so on. And so what I want us to work on here is doing 1, 2, 3, 4, 5, 6, 7, 8. I've got 8 different configurations we're going to do. We're going to do O2. We're going to do O2 star, first excited state. Then we're going to do N2. Then we're going to do N2 star, first excited state of nitrogen. Then we're going to do N2 minus. Then let's do N2 plus. Then let's do F2. And then let's do F2 star. So we've already done O2. We did not do N2 yet, but we did F2. So now the challenge is really going to be getting these excited states. Okay? And so you can pause the video and you can work with me if you like. Or excuse me, you can pause the video and work at your own pace, or you can listen to this music while I work through this. And I think what I'm going to do is just focus on one set at a time. So here I'll focus on the oxygen set, and then after that we'll focus on the nitrogen set, and then after that we'll focus on the fluorine set. Okay. So let's do that oxygen set first. Here we go. Okay, folks, so I've got the oxygen set and the nitrogen set worked out. So hopefully what you came up with, again, we did this one already, right? Triplet sigma G minus. So hopefully you came up that so this is the tricky part, right? Deciding what's the next excited state. And it's tempting to start promoting that up to the next level, which you can, and that would be an excited state, but that might be like the second or third excited state up. I'm going to introduce a final molecular term symbol so we know the order of energy of these excited states. But the correct first excited state would be forcing these two electrons to pair up. And when you do, that creates the delta state. So the fact that they're both in the same pi state, it's a +1 +1. Remember, over here it was +1 -1. That's what gave us sigma. So this actually gives us the singlet delta state. Okay? And so now if we do the N2, you should have gotten a 1 sigma G plus for N2. So remember that 1 pi U is the lowest energy. Okay? And so now when you're looking at what's the next excited state, well, would be to promote one of these electrons either to the Y or X. It doesn't really matter which. And then, of course, you might ask, well, what happens if this was spin down and it made the singlet state? Well, that would be slightly higher in energy than the triplet state. Remember, triplets are slightly lower in energy than singlets. So you should get the triplet pi G. When you do N2 minus, you just have to add one additional electron. And when you add one additional electron, that creates a doublet in the pi state, for which we want to notate whether it's 3/2 or 1/2. And we're only really concerned with doing that when we're creating that doublet state. Okay. So now I'm going to move on to the F2, and when I go on to do the F2, that's where I'm going to introduce a new type of term so that we can decide what's the correct order of energy for these things. Okay, so I'm going to go ahead and erase, and let's do F2 and F2 excited state. Okay, so get all this stuff here. I really like these sharp point pens, but I'm not crazy about the wet erase. You can see it gets all over my hands. That's all right. Okay, so now let's do F2 here. Okay, where do we go? Here we go. So now my F2, my F2, okay, is gonna look like this. And remember, this is the one where the order is 2 sigma G, then 1 pi U, then 1 pi G, then 2 sigma U. Okay? And if you recall, we have 10 total electrons to put up in this level. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's a closed shell, right? It closes out the shell. So we know that's going to be a 1 sigma plus G. And if you're wondering where I got that so quickly, remember that's the term symbol for anything that's got a closed out level. So the fact that the 1 pi G level was all closed out, 1 singlet sigma pi G, okay, with a bond order of 1. So now if I go to do this next excited state here, okay, here's where we can start having fun breaking the rules. Okay, 2 sigma G, 1 pi U, 1 pi G, 2 sigma U, and we're going to add our 10 electrons, and then now it makes sense that I promote one up like that. Okay, that would be the next excited state. And then when I go to calculate that term symbol, okay, what I want to consider, because I've got all of these open levels here, I'm just going to sum up everything from those 4 electrons. So my lambda is going to be +1 + 1, -1, and then +0 for the sigma. So that's going to be 2 - 1 = 1. So therefore, it is a pi state. Okay? And then we also recognize that it makes a triplet, right? Because those are both spin up. So that's a triplet. And then now it's a G times a U. So that gives me a U. Okay. So, well, how do I make my next excited state? What if I wanted to keep going here? All right. Well, what we could get, you might guess, would be to actually create the singlet state, right? So we fill those levels up, and then one here, one here, one here, and then now, if we force that to be a singlet, and so that would actually be singlet pi u. And so if we kept going with this, if we kept promoting electrons, we're going to have some kind of an organized way of telling us what's the correct order. So here's how we do it. We put a capital X in front of the term symbol to tell me that that's the ground state. Okay? So anytime I see capital X in front of the term, this is specifically the ground state, and the ground state of F2. So now when I go for the next excited state, I'm going to use the letter A. And I've seen some places not totally pay attention to capital letters or uppercase letters. But technically, when you have triplets, you're supposed to use an uppercase letter. All right? So this would be the first excited state indicated by A. And now it might seem logical that you want to do a B right here. But because this is the first excited singlet state, we're going to do a lowercase a. All right? And so now if I were to go and make the next excited singlet state, then it would be a B and then a C and then a D with whatever the term is. Okay? And then, of course, the next excited triplet states would be capital B, capital C, capital D, etc., next to whatever the term is. And this is where it gets really hard. As you start going up through the levels, it can become really, really difficult knowing which one is, in fact, the correct term. Okay, and furthermore, so I'm going to show you we have to do some calculations. And that's really what the videos that I'm going to share with you all are about how to make these kinds of calculations. Which is not my field of expertise, so that's why I'm going to show you some videos on how we get that. But one thing that I do want to point out, if we were to go and look at the bond orders of all of these states, as it turns out, 0.5 and 0.5, right, because that's 1/2 times 1, 2, 3, 4, 5, 6, 7, right, or nope, excuse me, that's antibonding, 6, minus 1, 2, 3, 4. Wait, 1, 2, 3, 4. Yep. So that gives me a bond order of, what did I do wrong here? Hold on one second. So here we go. 1, 2, 3, 4, 5, 6 minus 4. Yep, times 1/2 gives me 1. So over here, that's going to be 1, 2, 3, 4, 5, 6. Minus 1, 2, 3, 4. I did something wrong here. Well, in any event, if we were to go and calculate the energy of these states, okay, what I'll show you is we would get for our, now this is driving me crazy. Why did I not get that bond order correct? So bonding, antibonding, bonding, antibonding, 1, 2, 3, 4, 5, 6 bonds. Okay, well, in any event, I'm going to have to think about that and get back to you guys. I'm having a hard time thinking on my feet right now. So anyways, this is what that ground state looks like. And if we were to go look at that triplet pi u state, as it turns out, so, and again, remember, this is energy and this is bond distance. So that would give us our average bond energy and our average bond distance. Well, that triplet pi u state looks kind of something like this. It has a minima. It has a different bond length and different bond energy, triplet pi u. But as it turns out, this singlet pi u is entirely an anti-bonding state. So it actually has no minima. That's the singlet pi state. So it's a repulsive state. So we can start to predict this by looking at the energies of these various terms. And I'm going to switch over now to a document to show you a few examples here. So here I have someone who's calculated all of these states. And now granted, this is for bromine. So sorry, I'm getting my desktops all situated here. Okay, so now what you notice, even though this is for bromine, this is still pretty cool. I think I can actually put our work down here all on the same desktop. Yeah, here we go. So we recognize for bromine, it's still going to have the same configuration. Look, and there's that capital X telling me this is the bromine ground state, X singlet sigma G plus. And then now this is pretty cool. As we go up, we can see the next level is the A state, and then the B triplet. Here now, technically, this person put C, but they should have put a lowercase a. And I'm going to give you another example of that in the same document here. These are all of the nitrogen states. And what I want to point out here, look at this. I mean, just this mess of stuff is N2, and then here up here is N2 plus, and then buried in there is N2 minus, and this gets complicated. So I'm going to zoom in really quick so we can see what's going on. So if you recall, when we did nitrogen, let me pull that back up. Yes, this was my nitrogen. We came up with that it's supposed to be the 1 sigma G plus. And so there it is, the 1 sigma G plus. And then notice the use of the X to tell us that that's the ground state. Okay. And then here, this curve on this diagram is supposed to be N2 minus. And so remember the N2 minus, let's see. Yes, we came up with that it's the doublet pi 3/2 or doublet pi 1/2. So they ended up using the G term instead of the 3/2 or 1/2 term, which is fine because it's an unstable state anyways. But they still used the X term to indicate that was the ground state. And now as we keep going up, we can find that, yes, our N2 excited state was a triplet sigma G. But look, as it turns out, we didn't do this correct because that's the B state. As it turns out, a lower energy state is actually to make a triplet sigma, and that would be revealed through calculation. That would be really hard to predict. So you can't necessarily always predict correctly through the molecular orbital diagrams what's the lower energy states. So sometimes they have to be calculated. But that's why we have these letters that go in front. So then now we can see the capital A triplet, the capital B triplet, and then this is interesting. We get B prime triplet, and so that's from changing the symmetry operation. So this gets complicated, okay? And so I'm not going to hold you to a whole level of complication, but recognizing these terms, recognizing the use of the letter in front of the term so you know the excited states, I do want you to be able to do. Let's see, and then I'm going to cover molecular selection rules very briefly right here, but then in more detail as we get into the various forms of spectroscopy. So our selection rules, they're very similar to what they were for, actually, you know what, let's start a new slide. So they're very similar to what they were for atomic terms, okay? And we're nearing kind of the end of getting into a lot of our details on quantum mechanics and kind of going into more of the spectroscopy techniques, okay? So our selection rules with molecules, okay, so delta lambda can only be 0 or plus minus 1. So that was very similar to atomic terms, where you can go from like an S state to a P state, but not an S state to a D state. So what that means is you can go from a sigma to a pi, or a pi to a delta, but not a sigma to a delta. And of course, you can go to sigma as well, or pi to pi. So multiplicity, so that's a delta S, multiplicity must be 0. So again, just like saying we can go from singlets to singlets, doublets to doublets, and triplets to triplets, but not the other way around. And then finally, in that omega state, so that's equivalent to our J, we can go by 0 or plus minus 1/2. So you can transition from the 1/2 state to the 3/2 state, but not from the 1/2 state to the 5/2 state. And now what I want to say with molecular selection rules, unlike atomic selection rules, the selection rules in molecules can often be broken. And that's because if the center of symmetry is eliminated by an asymmetrical vibration, you can accommodate some of these angular momentum restrictions. And so what that means is forbidden transitions are often observed in molecular spectroscopy. They're just very, very low intensity. Okay, so for example, if I show you like a fictitious spectrum right here, perhaps we get one feature with a really high level of absorbance, so this would be absorbance, right? But suppose we have another feature that's very low in absorbance. Oftentimes, this is going to be the forbidden transition, and this is going to be the allowed transition. And so we might observe the forbidden transition just very slightly, but the forbidden transition only, we would observe the allowed transition very strongly. And an example of this would be like a pi to a pi star transition. So going from a pi bonding state to a pi anti-bonding state, that's an allowed transition. But as it turns out, an N to pi star transition is forbidden. And so that is going from like a lone pair state to a pi anti-bonding state. So as it turns out, that doesn't satisfy the lambda condition. So there ends up being a jump of 2 lambda units for that. But it's often still observable, just at very low intensity. Okay, folks, I think I'm going to wrap that up for this lecture. So this will be the only lecture that I record for this particular week. And what I'm going to do is post a series of small and short videos on variation methods and approximation methods. And those are the methods that allow us to calculate these really complicated looking diagrams and how we can predict what's lower in energy. It also allows us to calculate the molecular orbital diagrams of heteronuclear atoms. So I want you to watch those videos briefly. I think they do a really nice job of just hitting the conceptual points. And I will generate a few quiz questions from those other videos as well. All right, folks. And so I have made a PChem only office hour at now 11 a.m. on Monday through Friday. Okay, so 11 a.m. Monday, Tuesday, Wednesday, Thursday, Friday. That'll be a PChem. It's technically PChem lab, and seminar office hour, so it's like an upper division office hour. All right, folks. See you later.